Okay, let's work some homework problems here, or homework type problems at least. So, first one, let's just find a linearization of, say, f of x equals x cubed minus 2x plus 3 at x equals 2. Okay, and this is just find a tangent line. That's all that this means, right? So we're going to find the tangent line at x equals 2. So we're going to write L of x, because that's what the book is calling these things. I like t because it's a tangent line, but linearization for L, that's fine too. So this is going to be f of 2 plus f prime at 2 times x minus 2. Right, so that's just our point slope form, right? So there's our slope, x naught, x1, or sorry, x naught, and this is y naught. We move the y naught over by subtracting or adding on both sides, but this is what we got. We got our starting point plus the slope plus how far away from the starting point we are. That's how lines work, right? Okay, so let's fill in these things. If I put 2 into this expression, we get 8 minus 4 plus 3, which is 7. So this is going to be L of x equals 7 plus, I need to take the derivative, f prime at x is 3x squared minus 2. So if I evaluate that at x equals 2, we get 12 minus 2 is 10. So I got 7 plus 10 times x minus 2. There's my linearization. I can simplify this a little bit. It's going to be 10x. That's going to be minus 20 plus 7 is minus 13. So there is our linearization at 2. That's that one. Okay, let's do another type of problem. Let's use a linearization for an approximation. So let's say I want to approximate f of x equals x over x plus 1. We want to approximate that at at x equals 1.3. So what we're going to do is we're going to find a nice value near 1.3. 1 seems like a nice value. So we will linearize at x equals 1, and then use that linear approximation to evaluate at 1.3, giving us an estimate for f of 1.3. Okay, so I've got L of x equals f of 1 plus f prime at 1 times x minus 1. Okay, f at 1 is 1/2. If I put 1 in there, I get 1/2, right? 1 over 1 plus 1 is 1/2. Okay, plus I need to take f prime. So this is going to have to be a quotient rule one. So f prime at x is low d high minus high d low over the square of what's below. So I've got an x, plus 1, a minus x, so the x and the x cancel. This is just going to be a 1 over x plus 1 squared. If I plug 1 in there, I get 1/4. So 1/4. So f prime at 1, 1 over 1 plus 1 squared is 1/4. And then I have x minus 1. So I'm going to take 1/2 plus 1/4 of x minus 1. So L of 1.3 equals 1/2 plus 1/4 times 0.3. So it's 3/10. 1/2 plus 3 over 40 is 23 over 40, which I can calculate. 1 over 40 is 0.025. It's 2.5 40s give you 100, so it's 2.5 100ths. So this is going to be a 0.675, I believe. Let me put that into a calculator and check. .575. I was a little bit off. Okay. 575. Yeah, that makes more sense. Okay. So there's our approximation. So we know that 1.3 divided by 1 plus 1.3 should be approximately 0.575. Let's use that calculator again to see how close we were. So I've got 1.3 divided by parentheses 1 plus 1.3, and we get 565. So a tenth off, which that's pretty good for not actually doing the division. So let's see another one. Let's go with find a derivative in differential form. So we want to find dy if y equals, say, let's do one where we have to do some implicit differentiation. Let's go not y equals then, but got 2y to the 2/3 plus xy minus x equals 0. So we want to find dy. So we're going to do just implicit differentiation. We're going to find dy dx, and then we're going to get dy by itself by moving the dx to the other side, basically. Let's actually do the book problem that says 3/2, not 2/3. Okay. So differentiation on the left, I've got 3 halves times 2 y to the 1/2 dy dx by the chain rule, plus I've got a product rule here, so I've got y plus x dy dx, and then I've got a minus 1, and that's equal to 0. So I want dy dx by itself, so we'll collect the dy dx stuff on this side. We're going to cancel those 2's. So I've got dy dx, and then I've got a 3y to the 1/2 plus x, and then we'll move this other stuff to the other side, so 1 minus y on the other side. So dy equals 1 minus y over 3y to the 1/2 plus x dx. That's my differential. Okay. Let's approximate an error. Let's say we've got f of x equals x squared plus 2x, and we evaluate f of 1.1 as approximately f of 1, and we want to know how much that might be off approximately. So f of 1 is going to give me 3. So f of 1.1 should be about 3, but it's going to be off by a little bit. And how much off is it going to be? Well, we're going to have dy is equal to 2x plus 2 dx. Well, x is off by about 0.1. So that's going to be what our dx is. X is equal to 1. So dy is going to equal 2 times 1 plus 2 times 0.1, which is about 0.4. So we expect the error in this to be about 0.4. Right, so let's do the actual calculation to see how close our error was. F of 1.1, well, that's equal to 1.1 squared plus 2 times 1.1. Okay, so this is 1.21 plus 2.2, which is 3.42. Our error here is pretty close to what we thought it was going to be, right? We said that the error was going to be about 0.4. The error was exactly 0.42. So that was a pretty good estimation for our error there. Let's do one more of these. So we want to write a differential formula that estimates the given change in volume or surface area. So let's write down what this thing says. The change in surface area, which is equal to 6x squared of a cube, when the edge length changes from x naught to x naught plus dx. So that's how much it's changing. We want to estimate the change in the surface area. So we want ds, and ds is going to be equal to 12x times dx, right? So in dx, we're there, and I'm just going to put a naught on that because that's where we started. So that's exactly what we have. So if I wanted to get a specific situation here, say the cube had side length say 3, and it now has side length pi, we can estimate how much that surface area has changed by the change in the surface area is going to be approximately, well, so I should put the approximately here. The delta S, the actual change in the surface area, is approximately the differential, and that differential we just wrote down is going to be 12 times 3 times 0.141 dot dot dot, right? So we're just going to be estimating it at 12 times 3 times, let's just estimate it at 0.14. 3.14159, yeah, okay. Which is 36 times 0.14, which is about 5. So the surface area will change by about 5. Let's do that calculation. So the original surface area was 6 times 3 squared, which is 9 times 6 is 72. And 3.14 squared times 6 is approximately, let's pull up that calculator again. Clear, 6 times 3.14 squared. And 6 times 9 is not 72. That's 8 times 9. This is 54. Good thing I don't always have to do arithmetic in my head. Okay, so we went from 54 to 59.1576, right? And we have approximately what we said it would be. Maybe I can get a better estimate by taking 36 times 0.14. Whoops. Where's my calculator again? Uh, 36 times 0.14. 5.04. So maybe slightly better because I am at 59.04 rather than 59.15. So slightly better when I did the actual more full thing there. Okay, So those are the type of problems that you're going to have to do on the homework. I will see you guys in class tomorrow.